In the last video series, we did geometric optics for systems of a single mirror. Here we'll focus on a single lens. So first, we'll start by just plain talking about what a lens is. Usually, it is a piece of material. It's a piece of material usually of higher index of refraction than the surrounding medium, although that's not required. But usually this is air. Usually this is something like glass or something like that. But other possibilities are there. And the idea is, let's say we have a ray of light coming in like so. Oops. We'll draw, oops, my bad. There we go. So we'll have a ray of light coming in. Now officially what happens is it'll get to this first plane here. We can drop in a normal and see we'd have to bend in toward the normal. So much like when we were doing the raindrop for the rainbow. It'll bend in, do something like this. And then it will, it's a little too much. It'll bend in a little bit. Yeah, maybe something like this. And then it'll bend away from the other normal, which is pointing like that, and go through focal point. So that's what happens officially. And if the lens is actually physically thick, that is how you have to handle it in practice. But it turns out that for most lenses, you can get away with pretending that they are quite thin. And then you can go ahead and apply the thin lens approximation. Oops. This says that you can pretend that all refraction occurs at what's called the principal plane of the lens. And for most practical lenses, this is an excellent approximation, and there's nothing wrong with it. So we'll go ahead and do that pretense ourselves. Oops. Sneak that in there. There we go. So we'll go ahead and do that little pretense ourselves. So we can draw a ray coming in. And here, this is an approximation, but it's an excellent one. If I have some paraxial ray coming in, we'll pretend that it does all the refracting at the principal plane and goes through. Of course, like I say, in reality, it refracts once at the front surface, once at the back surface, but this is what we pretend. And if our lens is well designed, any other ray that's parallel to this ray will also bend through the focal point and so forth. Let's do a few rays down here just to get the idea. And then, just to make a bit of a point, when we do constructions, sometimes it may be the case that the ray you draw doesn't actually hit the physical lens. For purposes of doing a construction, you can still pretend that it goes through. So this ray doesn't actually happen, but you can pretend that it happened. Okie dokie. So I'm just going to copy my lens here. And so, much like we were doing with mirrors, there is a construction you can do to relate object and image distances, focal lengths, all of that. So that's what we're about to do. Oops, don't want to delete my focal point. You'll notice too that I actually drew in 2 focal points. This is because in the thin lens approximation, the lens works the same frontwards and backwards, so it's symmetric that way. There we go, nice and clean. So again here, I'll just go ahead and draw myself what will correspond to a case 1 situation. Again, we're only going to draw a couple of rays, and then we will later get more detailed about how we actually do this. So let's park our objects, say, out over here. So the 2 rays that I'm going to need to get all quantitative about things is going to be the paraxial ray, which we'll take to the principal plane, and then from the principal plane we take it to the focal point. The cartoon of the lens is only to remind us if it's converging or diverging. In the central ray, it turns out that a ray that shoots through the optical center of the lens does not get diffracted very much at all. So in the thin lens approximation, we just go ahead and pretend it doesn't get diffracted at all. Okay. And normally when we do a ray diagram, we draw a 3rd ray to check our work. But here I'm just locating my object and my image. So this is going to be my object distance, and it's positive in this example. And this here is going to be my image distance. And in this example, it's positive. In the left-like convention, signs are positive if they're where the light is, and negative if it's where the light ain't. So here we're going to be forming a real image that can be formed on screen. So in this example, this would correspond to a positive image distance. And just like before, the object height here will be HO, and the image height here will be HI, and in this example it's negative because the image is inverted. And it turns out that once again, just like we did with mirrors, there are a pair of similar triangles that we can look at. One pair is, whoops, I did not, pardon me here. One pair, so I'm highlighting here in green. They have a right angle in common here and here, and because the central ray goes through undeflected, those angles are in common, so these wind up being similar triangles. And also, switching colors here, this pair right here, this is similar to that. Again, oops. There we go. Again, right angle here, right angle there, by alternate interior angles, those angles are the same. So therefore, those are also similar triangles. And just like I alluded to before, if you set up the proportions, do the tedious algebra, you'll get that the magnification, which is HO over HI, is equal to minus DO over DI. And once again, the most useful equation in optics shows up, 1 over DO plus 1 over DI equals 1 over F. So it's the exact same results that we got before. And again, it is the exact same sign conventions that we used before. So I'll just refer you to the previous video on them. But again, just remember, upright is positive, inverted is negative. If the image is real, it's positive. If it's virtual, it's negative. In this class, object distances will always be positive, although virtual objects are a theoretical thing. And we would have to worry about them in a more advanced class, but not here. Yeah, so, and focal lengths are positive if the lens is converging, like the one I've drawn here. Negative if the lens is diverging, and we'll see an example of a diverging lens. Okay. Now I want to make it clear that converging and diverging can take a lot of different meanings here. So with radii of curvature, if the light hits the surface before it hits the center of curvature, it's positive. And if it hits the center of curvature before it hits the surface, it's negative. And I bring this up because there's what's called the lens maker's equation. And the lens maker's equation. And again, I'll dispense with the derivation. It's rather tedious, and I don't feel it's all that terribly instructive. But it allows us to calculate what the focal length of any lens would be. And it'll be equal to the index of refraction of the material you're making the lens out of over the index of the surrounding medium. This is usually air, and so this is usually 1. Minus 1 over 1 minus 1 over R1 minus 1 over R2, where R1 and R2 are the two radii of curvature. So I already drew an example of a converging lens, one that would give us a positive focal length. And that was this sort of a shape here, which gets called a biconvex lens. It just means it's convex on both sides. Here, as the light's coming in, it strikes this surface here first. So this is surface number 1. Then I'll hit this surface here. Now surface number 1, this point here the light coming in from here will hit the surface before it gets to its center of curvature. Therefore, this R1 is a positive number. By the same token, this light here, well, the center of curvature for surface 2 is out over here. So the light got to surface 2, to the center of curvature, surface 2, before it got to the surface itself. That makes it a negative. Putting into the lens maker's equation, R1 is positive, R2 is negative, positive minus a negative is positive. We're going to end up with a positive focal length. But other shapes are possible. Let's say you had something, there we go. Let's say you had something that looked like this. Flat on one surface here, and then curved. This is called a planar convex lens. And here with this surface, this R1 here, would be equal to infinity. You put in the infinity for R1, this 1 over infinity would become 0. Plain very loose. But other shapes that you might not expect, very common in eyeglass design, is what's called a meniscus design. So this is an example of a meniscus convex lens. And yes, the two surfaces are kind of fighting each other. They both have positive radii of curvature. So they are fighting each other. So it's so yeah. If all you want is to get focal length, this probably isn't the shape for you. But the reason for its choice, for its popularity in eyeglass design, is that the thickness of the lens stays the closest to constant across the whole lens. This helps to minimize distortion when you're looking through lenses, and so that's why, through your eyeglasses, and so that's why it's a popular choice. We could also go and look at a diverging lens. So with diverging lenses, the focal length is negative. And so I'll just draw a few quick examples. This will be the cartoon I'll probably draw the most. This is what's called a biconcave design. Now here, this is still surface 1. This is still surface 2, but now the light got to the center of surface 1 before it hit surface 1 itself. So it makes R1 negative. And here the light got to surface 2 before it got to the center of curvature. So it makes R2 positive. Going back into the lens maker's equation, negative minus a positive is negative. We're going to get a diverging lens. What we'll see is parallel rays of light will come in, and they'll spread away from a focal point. We could just as easily do something like build ourselves a planar concave lens. Say something like this. And if you're nearsighted, your glasses are going to look something like this. This is called, whoops, there we go. This is called meniscus concave. And again, it's the same idea. Both radii of curvature are again positive, but the difference is which one's the bigger radius of curvature. So something to notice. For all these lenses, the converging lens is fatter in the middle. And for diverging lenses, they're thinner in the middle. That is as long as the surrounding medium has a lower index of refraction than the lens. I mention this because there are pathological cases, like sometimes you'll put special lenses into certain kinds of oil, and it could be possible that the index of the oil is higher than the lens. Sometimes people will, for certain applications, will intentionally make a lens by making a bubble of air inside, say, some glass or something like that, with the bubble being cleverly shaped. In those cases where the lens has a lower index than the surrounding medium, then the roles of converging and diverging are swapped. But that's incredibly rare. That's just something that you should be aware of, just in case you ever run into it. But this is, so all these shapes are for n greater than the surrounding medium. Okay. So, just like before, it turns out that you have the exact same 4 prototype cases that you did before. for drawing ray diagrams. So let's go and start drawing ray diagrams. Oops. So, and when you're drawing a ray diagram, the only thing that really matters is the principal plane. So I usually don't sweat doing a good job of drawing the lens. I just draw one in just to remind myself of whether I'm dealing with something converging or something diverging. Now, because of this, in the thin lens approximation, it's symmetric, you have to draw a focal length on both sides now, because now the light is passing through. So in case 1, it'll still be the case that DO is greater than 2F, and we're still requiring that F be positive. All right, so let's draw our object more than 2 focal lengths away. Yeah, this looks pretty good right here. So for lenses, there's really only 3 rays that are good, unlike mirrors where you've got that 4th bonus ray. So we can start with, again, the paraxial ray. It'll come in parallel to the optical axis, and again, you take it straight to the principal plane. In reality, it will diffract first at this surface and then at that surface, but we just pretend all the action happens at the principal plane. And that one will refract right out the focal point. Now again, if we were to reverse this, if we were to imagine, say, some ray that was coming in parallel like this and refracted through the focal point here and just grazed the top, if I time reverse it, it's got to work the other way around. So once again, we will have the focal ray is the ray that is aimed at the near focal point, like so. You take it to the principal plane, and then that ray will go out parallel. And then to check your work, the central ray is your truest, bestest friend, and this one is really straightforward to draw. It just shoots right through the intersection of the optical axis and the principal plane. Alrighty, and we see that all 3 rays basically came to the same spot. Oops. So we can use that to locate our image. And just like it was the case with mirrors, this is real, inverted, and minified. And again, just like before, I'm going to ask you to construct the case 2 situation, which is where DO is between F and 2F. And again, we're still dealing with a converging lens. So go ahead, pause the video, try to construct the ray diagram, and then we'll meet back up. Alrighty, so here's my attempt at it anyway. Alright, let me clean that up for a second. There, not too bad. So here, the object now is going to be located between F and 2F. So we'll go and park our object a little closer to the focal point than we did before, but we're still outside the focal point. Okay. And again, it's the same deal as before. We will draw our paraxial ray. There we go. That's pretty good. It will go out through the focal point. Our focal ray, so we're going to go through the near focal point, take it to the principal plane, go out parallel, and then just like before, we check our work with the central ray. That's still not too bad. Alrighty, and we locate our image. And sure enough, just like before, it's real, it's inverted, and it's magnified. Okay, on to case 3. So in a case 3 situation, the focal length is greater than the object distance, but they're still both positive, so it's still a converging lens. Oops. Actually, I'm going to want to draw in. Oh no, that's okay. I can kind of use this. There. Here I'm going to make my focal points a little further out, just to make it a little easier to draw. Something like that. And I'll stick my object, say, here. So focal point, focal point. So again, same deal. The paraxial ray, you'll take it right to the principal plane, and then again, right out the focal point. Now with the focal ray, same deal. Now that we're inside the focal point, we have to project it out from the focal point like so that just grazes. So I'll just draw in some dots to help make that clear. So it just grazes, and we're going to take it out parallel, out in line with the focal point, and then we will refract out parallel. And then finally, the central ray is your truest, bestest friend. All right. Well, I think it's pretty clear looking at these that these are never going to converge. So we're going to have a virtual image. This means we'll have to look through the lens to see the image. So we need to backtrack the rays to see where they appear to come from. Not too bad. Yep, sure enough, right there. And what we get, so this is my object here, and this is my image, like so. And then now here, the image is where the light ain't. You can't form the image on the screen. So this image is virtual, upright, and magnified. So this would correspond with, say, Sherlock Holmes' magnifying glass. You look through it, it looks bigger. And then finally, again, just like before, case 4, will be the case for a diverging lens. So here's my optical axis. Here's my principal plane. Again, I'm just drawing a cartoon of the lens. So we're not really going to use it. All the action is going to happen at the principal plane. So we'll draw in some focal points here. But keep in mind that since the focal length is negative, that swaps the roles of the points. By that I mean the front focal point is now on the back and the back focal point is now on the front. So I often do something like draw a negative F when I label it, just to remind myself that this is the front focal point and that's the back focal point now. That's what the minus sign does for you. And again, we can park our object anywhere we want because it's going to be in front of the front focal point no matter what, because it's over there. Actually, just to prove a point, let me make the object ridiculously large. Let's say, yeah, that's good, like that. Now, why did I do that? I just want to show you that if your lens is small, if your ray doesn't hit your lens, not the end of the world. You can still pretend. Here, we'll do it more carefully here. You can still pretend that it's there. So I'm just dashing that in. There, that's pretty good. So even though this physical ray would not contribute to making an image, for purposes of calculating things, we can still pretend that that ray is there. Okay, let's go ahead now and do the focal ray. So the focal ray will be the one that is aimed for the focal point, like so. I'll just put in a few dots to remind ourselves of that. And that one will bend out parallel, just like it always did. And as always, the central ray is your truest, bestest friend. It always goes back, goes through undeflected. Okay, so if I backtrack the orange ray, it's just going to sit right on the orange ray. I've already backtracked in the red ray when I was showing where it's coming from with the focal point. So the only one I need to backtrack here is going to be the green ray. There we go. So there is my image. Again, it's where the light isn't, so you have to look through the lens to see it. That makes it a virtual image. It is upright, and it is minified. If you are nearsighted, you can take your glasses away from you for just a few centimeters, put them, say, like a few centimeters in, over some print, and you'll see that the image is shrunk down. Okay, and I thought I would end this one up by just doing one example numerically. So the one I thought up to do, whoops, sorry about that. The one I thought to do was to, oops, there we go, optical axis. Since I know that this one's going to end up being virtual, I'm going to shift the principal plane over to the right, because no, let's keep it more toward the middle. That'll be fine. All right, so let me label in the focal points. Yeah, about there will do. About there will do. There, that looks a little better. There. So we're going to do a converging lens. So our focal length, and it's the same on both sides, for this problem is plus 40 centimeters. And I'm going to go and stick my object at DO equals plus 30 centimeters. We'll also go ahead and say that the object height is plus 5 centimeters, plus because it's right side up. So I would like again here to locate the image and to figure out where it's located. Sorry, locate the image and figure out how high it is. And sorry here, but I need to move this just a little bit. There, that's closer to being about right. Okay. So again, when you're doing these things, you don't have to do a great ray diagram, but you should do a ray diagram. So let's just kick one out here, paraxial ray. And you already look at this and you know the object it's a converging mirror lens, and the object distance is less than the focal length. So we already know this is case 3. So we're expecting that's virtual, upright, and magnified. We can check our work. Oh boy, is it going to be magnified. So we can go ahead and check our work here with our ray diagram. And yeah, let's draw in the central ray, again, our truest, bestest friend. So yeah, who doggy. All right, let's see. I can already tell you that this artwork is going to be very bad. I must have stuck the object a little too far away from the focal point when I drew it. But yeah, let's go ahead and backtrack the rays just to get some feel for the, yeah, it might be all right. Backtrack the rays to get some sort of feel for this. Actually, you know what? That might not be too bad. All right, so based on our incredibly crappy drawing, here's my image. So I can already tell that the image height is positive. Positive, I don't know, but it's positive something. And since the image is located where the light ain't, it's negative, I don't know, but it's negative something. So we can figure both of those out. Looking at the drawing, I'm going to go and say, it looks to be, I don't know, maybe 3-4 times higher. It looks like it's set 3-4 times further back, somewhere in there. I mean, I wouldn't be surprised if this turns out to be a factor of 5 or something, but if it's like a factor of 20 or something, then I probably did my math wrong. All right, so again, same kind of deal as we did for our mirrors. Go ahead and start with the most useful equation in optics. So 1 over dO equals, plus 1 over di equals 1 over f. So 1 over di equals 1 over f minus 1 over dO. Put on a common denominator, dO minus f over dO times f. So this gives us that the image distance, di, is DOF over DO minus f. And here my object distance is a positive 30 centimeters. My focal length is a positive 40 centimeters. This will be positive 30 centimeters minus a positive 40 centimeters. So this will give me negative 120 centimeters. All right, looking back at the picture, maybe, you know, it wasn't the best drawn diagram ever, but at least it's consistent with the drawing. Okay, And again, we can use the magnification relation, so it will tell us that Miller magnification equals di over do, but that's also, sorry, minus hi is hi over ho, which is minus di over do. So it'll give me that hi is equal to minus di over do times ho. And again, you cannot drop the minus signs. Can't drop this one, can't drop that one. If you do, you won't get the right answer. So we get that the image height is minus 120 centimeters over 30 centimeters times plus 5 centimeters gives me plus 20 centimeters. And again, it's not the best artwork that I've ever drawn, but the answer is consistent-ish with it. So there you go. Okay, and with that, I'll catch you in the next one. Have a good one.